lab, we have this data set, exam 1, exam 2, and final exam. That's from my last year's classes. So 3 sessions, about it's 141 data points here. So the whole idea is we like to build a model which can use the exam 1 and exam 2 score to predict the final exam. Okay. So first, this is a simple linear regression model, which is in our curriculum. We built the model with just one input, one independent variable, which is average. Okay, we build the model. And then the optional project, not the lab optional ones. So I will provide a separate, say, assignment, optional ones. You use the multiple regression to build the model. So first, we prepare the data. So this is the very first thing is you look at any missing data points. Okay? Since it only have 141, you can visualize to see any missing ones. I think I already cleaned up the data. I already cleaned up the data. This is my previous analysis. So total 141 data points. Okay. So before you dive into this data to build the model, you need to visualize. So we call exploratory data analysis. It's like describe your data, what it looks like. We use a scatter plot to plot exam 1 versus final, exam 2 versus final. And also we like to see the average versus final. And then we build the model using average as our independent variable. So the first thing I will have one called scatter plots. So the first thing, certainly we can select the data, select 2 columns, and you hold it. And then you just select. Okay. So you select these 2 columns, insert scatter plot. Okay. So we add the access title. So this is exam 1. Okay. So we want this exam 1. This is the scatter plot for exam 1. And then we want this one. Exam 2 and the final exam. So we add the access title. Exam 2. Just put it here. And the next one, we want the average. Okay. Just the average. Okay. Of exam 1 and exam 2. So next, we like to plot average and exam 1, exam 2. Let's see. I can copy this column. So this make life easy. It's everything X on the left and Y on the right. If you don't do that, you have to switch X and Y once you generate the scatter plot. So we insert the scatter plot, and then we add the title. Oops. It's called average. So we look at this data. We like to build the simple linear regression model, use average to predict your final score. So it looks like a linear relationship, but it's not very strong, right? So next, based on this data, we build the model. Okay. What we can do, we like to copy to a new sheet. So this is we call regression or simple linear regression. Oh, we need to paste the, not copy. We need to paste the formula, the value. Okay, paste the value. Okay. So we have the data here. Okay. 142 data points. Now we have the simple linear regression model. Now we like to just view this as a true project. Certainly you can use this to say, try to predict your final score if everything as it, okay? If we just use these 141 data points to build the model, okay, it's very hard to evaluate how good our model. The common practice is to split your data into two sets. One set used to build the model, another set just used to verify your data, your model, so how good your model. We know if we use all this data, build the model, okay? So simple linear regression model may be not that complicated. If multiple is maybe more complicated, may have this overfitting issue. Okay? But for this one, we also like to go through the process to show how we verify the model use independent data set. Okay? So this is the purpose. The first thing we like to split the data set. So for this one, we have, we call it index. Okay. So how we do this, we need to randomly pick 70% data as the training data to build the model, and the other 30% as the testing data. We test how good the model. This testing data is totally independent from the data you build the model. So that's better test how good the model. Otherwise, you fit the model, that's your own data, okay? Your model and your data are dependent. So how we randomly pick 70% of the data points, we generate random variable, okay? Random value between 0 and 1. And then we sort it from small to largest. It's like we shuffle the data. And the first, so 70% see 141 multiply 0.7, it should be 98 data points. Okay. So once we have this, we can fix see, it's all random variables. We copy and paste the value. So that's good thing, we paste the value, it wouldn't change so it's not the function anymore. The function keep changing. The next thing, we sort the data. Sort the data from the smallest to the largest. Index. And then we just pick this first 70%, the first 98 data points. So it's down to here, the row 99. Okay. So above, all these are the data used for training to build your model. And this data, okay, we cut this data, we put here, we call the testing, we put here. And then we don't need this index anymore. The question. Oh, first, the whole purpose, I split the data set into two parts. One part used to build the model, training the data. That's 70% of data. That's 98 data points. The rest, 43 data points, used for testing how good the model. So I'm doing this. You have original data order. I just totally randomize it by adding one. Is that the question you have? You want me to go, or so you just put the random value here and sort the random value. It's like totally shuffled your data. Okay. I randomly pick the 98 data point for training and the rest for testing. Because this is the training data. And this is the test data. Okay. So the training data, we can now build the model, use regression, and then to use this data set final. Okay, that's the y-axis. 98 data points. So include the title, okay? 99 data points. You from like A1 to A99, and you have labels, and you check the label, okay? That's your title. You have the residual test, the normality, and output range you put somewhere here. I just put L1, okay? Or maybe you say M1 is fine. Let's maybe give more space. M1. Okay. Click OK. So this is your model. Okay. So this is the intercept. This is the slope from the model. And the p-value is quite small. That means it's significant that we do have the linear relationship. Slope is not equal to 0. And f-test, the ANOVA also shows the p-value is very small. So we do have the linear relationship. You see the r square, 0.56, but just not that strong. It's okay. It's like 56% can be explained by the model. Okay. So next, we like to see how we test how good the model in your testing data. Okay. So I need to remove this one to here, the testing data. What I want, we want this final predicted. Okay. In other words, this is y hat. Okay. So how you find out predicted one, that's equal to your, look at intercept, okay, and plus the slope multiply your average. And also, we like to put a $sign here. So now you have the new column, the predicted value. This is your original, the observed value. Okay. So what we like to have, the very first thing, what is the r square? So r square for the test data, okay? So we know the output gave us the r square just for the training data. So easiest way to for the testing data, r square. Just see r square. Just put a little further. R square value. Yes. Or predicted value, that's since you already built the model from your training data, you know intercept, you know average, right? Your y hat equal to the intercept plus so this is your average score. Right? So these two from the model output, intercept plus the average multiply the average result. And then you have the whole column predicted value. Okay. So the easiest way to calculate this R square for the test, okay? We just use there's one function called R square. So it said returns the square of the person product moment correlation. So our correlation coefficient have another name called person's correlation. Question? Yeah, index just random data, just a random between 0 and 1, and then you sort from small to the largest. That's just a way to shuffle the data, and like you randomly pick the data. Yeah, easiest way, you can have this R square. Okay. So this is the correlation, squared correlation coefficient. So we know so here we find out this column just from here. It's only the numerical value, okay? And then the predicted one. Okay. So R square value is this one. Okay. It's pretty good, okay, compared to this R square. Okay. Any questions? So what we used here, you also can, since this is simple regression, you only have one X, you also can use correlation, just use correlation and then squared. That's the same. You use R square, that's the same. It's just this R square is not the R square correlation between X and Y. So this is the testing data, the result. We like to see you predict and your original data, how much correlation there. Question?
How many values do you use for like the test data?
Test is 30%. So 43 data points in this one. We use 70% training. Sometimes people use like 80-20. Yeah. So this just to show us how good this testing shows how good your model. Okay. So the model explained 65% of the variation. Okay. It's not super good, and it's okay. So next thing we evaluate how good we call mean squared error. Okay. And also have the, we call the square root of mean squared error. Okay. So how to find out the mean squared error part? So what is the error part? So the error part, that's your observed value, the difference between observed and your predicted. Okay. That's the what we call residual part. The mean squared error. So this is just the error part. And then divided by the minus 2. That's your error. That makes sense? So we need to find out we just use y minus y hat, predicted ones, and then squared. Okay. So that's equal to, this is the true value, the original value. This is the predicted from the model. So we like to know squared variance. Okay. And it's automatically filled. And then this equal to, we just sum all this together. Okay. And divided by sample size here, we have 43. That's data n minus 2. Okay, 43 minus 2. Actually, here we don't need to 43 minus, just divided by 43. My fault. Okay, the reason, because this testing data, we do not use testing data to build the model. Because the model we use training data, so we do not lose any degree freedom. Okay. So that's why. Another thing we like to see the square root of the mean square error. Okay. See, we take the square root. So what does that mean? The square root of, this is the, on average, the squared, the error part. You take the square root, we down to the unit, the same unit as your data is not squared, right? So this, on average, you predict the value, okay? So how far away from your true value, your original data, is 9 points. So this gives us the idea how good your model, you are going to use it to predict, right? And how much you can trust. So you use this testing data, you say, okay, it's like, if you predict you are going to get 80, so that means the range is like, yeah, on average, yeah, could be from 71 to 89. That's your possible, sort of have the idea. So how good this prediction. Okay. So once you have this, we're done with this. And also we need to check the residual to see. So that's we done with the Excel part. Okay. We use Excel to do the job. Let's see. It should have the plot here. It's not here. So that's the lab. We just use the linear regression in Excel to solve the problem. So any questions? So you're done, you just submit, and then you're done with this lab. Okay, so we have some time for the second one.